All right, can y'all see that now? All right, here we go. Two 25 Newton weights are suspended at opposite ends of a rope that passes over a light frictionless pulley. The pulley is attached to a chain from the ceiling. What is the tension in the rope? What is the tension in the chain? Okay. All right. Well, let me minimize this and let's draw it, and then I'll come back to it. Okay. So we've got two weights, and of course you need to always draw it. You know that. There's your pulley. Got one here, one hanging here. The weights are 25 newtons. This one's 25 newtons. That's the weight. And the weight of this one's 25 newtons. Okay. All right, now it says what is the what is the tension in the rope? So we want to know T. We want to know T, don't we? Okay. All right. We want to know T. All right. Now, we got to do some analyzing. All right. Are these weights accelerating? Okay. So then that tells us the sum of the forces are equal to what? 0. Okay. All right. So then that means what? T minus mg is equal to what? 0, isn't it? Right? Now, why did you write mg? Look, tension is which way? That way. Mg is which way? This way. All right? Mathematically, y'all, if I draw my axis right through there, you follow me? Down's negative. Okay, y'all. Then what's the tension in the ropes? T is equal to mg. Well, what's the weight? 25 newtons, right? Huh? Each one's 25? Look. 25, 25. Each one's 25, right? All right. Now that's for the ropes, right? That's A. This is A, right? Does everybody see that? I know there's two, but you got to realize that pulley, they're hanging individually. Even though they're on a pulley, there's still one over here and one over here. Okay? The amount of tension on this rope can't be any greater than the amount of tension on this rope. Because why? The masses are the same. Okay? And it's not accelerating. Yes. Mm-hmm. So the tension then is going to be what? 25 newtons. And that's on both ropes. Right? Now, if it was accelerating, y'all, it would be different. Remember the elevator problem? Okay? It'd be different. All right. But now, wait a minute. What about the chain? Now, this is here. Now, notice there's tension right here on the chain. This is part B. Now, see, y'all, this is why you got to draw the diagrams and label your forces. Now, it's a little bit different. All right, look, we've got mg here. We've got mg here. How many mg's is that? 2. But we've got one, how many? 1t, right? Everybody see that? We're talking about the chain now. Forget the ropes. They're gone. Well, they're not gone, but they're not. Okay? We're looking at how much is on the chain, all right? So T minus what? 2 mg is equal to 0, so T is equal to 2 mg. Well, mg was 25, so T is equal to what? 50 newtons. See, that problem looked hard, but it's not. Does everybody see that? 2 mg's. You got 2. Now, here again, y'all, if it was accelerating, this problem would be different. You'd have to put equal to ma and then go from there. And know the acceleration, right? And then find the mass for each one, and then go from there. All right? Okay. Actually, be an Atwood machine problem. And we actually got one we're going to work. I don't know if we'll do it today. We may wait and do it. May wait and do it Wednesday. I don't know. We'll see. Okay. All right. Any questions on that? All right. Number 3. Ooh, yeah, that's a good one. All right. Number 3 kind of makes you scratch your head a little bit. All right. Let me go back to this, and let me pause the. Keep. Pause. Okay, now. All right, so we have what? So we have, well, what number is this? Number 3? So we got our boom here. We got our, this is 26 kilograms, the mass of the chain. The wrecking ball was 70 what? 5 or 6? 5. Yeah, mass of the wrecking ball is 75 kilograms. That's cool to watch if you ever watched them tear a building down with a wrecking ball. That is crazy. Anyway, all right. All right, so we know the sum of the forces is equal to what? 0, because it's not accelerating. Y'all, you've always got to determine that before you do anything. Always. Before you do anything. Am I accelerating? Yes. Am I accelerating? No. If it's accelerating, it's equal to ma. Because, y'all, if you don't, you're not going to get these right. You've got to do that before you do anything, after you draw it. All right, now. So, where's my tension? Tension is what? Up. What's down? mg, right? That makes sense. Okay? All right, but now notice we've only got mg here, but we've also got what? mg right there too, don't we? Right? So how am I going to write my equation? T minus what? There's a couple of different ways you can write it. And I'm going to write it this way. Come on, y'all. Let's use our math smarts. Let's be math smart. Factor out a g, right? Because mg and mg, well, g is the same, isn't it? They're both going down, right? Can I add those together? Since they're both going in the same direction, can I add the two masses together? M of 1, let's say this is 1 and that's 2, plus M2 times G is equal to 0. Can I do that? Can we do that? That's math sensible, right? Yeah. All right, now the physics is over with. So T is equal to what? M1 plus M2 times G. So plug everything in. So we got, now this is max. So we got what? 26 plus 75 times 9.8. And what do we get? 990, is that right? 990. All right, what do we get for minimum? Well, okay, minimum is just going to be what? T minimum is just going to be the wrecking ball, isn't it? So it's going to be T minus mg is equal to 0. T is equal to, and that's M2. So that's going to be 75 kilograms times 9.8 meters per second squared. And what do we get? 7 what? 735? Everybody get that? Yeah? Everybody sees why we leave the 26 off. We pull the ball all the way up, there's no more chain. There's no more chain mass. And you say, well, how can you say that? Remember, y'all, the pulley, the mass of the chain now is on the other side of the pulley. We're not supporting that mass. The only mass we're supporting is the mass of the wrecking ball. Okay. Actually, we are supporting a little mass of the pulley. We want to get real technical, but again, we're going to ignore that because it's not enough to make a big difference here. It's not going to make that big of a difference. Okay. In engineering school, it will make some, and you'll do that, but it's not going to be huge. It'll be a little bit, okay? All right. All right. Okay. Okay. Any questions on that? Now, what was the next part? Oh, shoot. Oh, yeah. What is the tension at a point 3/4 the way up from the bottom of the chain? Okay. All right. First thing we got to do is determine what? The mass of the chain 3/4 the way up. And what is 3/4 the way up? From here to there, right? Okay? So in other words, if you pull it up just a little bit, or maybe I should come from here down to there, you're going to have 3/4 of the chain still hanging. All right. So we got to do what? Mass of chain is what? 3/4 times 26, and that is what? 19.5 kilograms? Then we go back to our first equation. Now we've got 19.5 kilograms plus 75 kilograms times G, and we get what? 926.1. Notice how the chain doesn't affect the force that much, does it? It does some when you pull it, when you take it all out, it does, somewhat. But still not a whole lot, does it? 735 to 990, it's not a huge difference. Okay. Yeah. And then if you want to look at, you say, well, how much force will that thing make when it swings that boom? Well, that's where you have to look at centripetal force and the velocity it'll have and how much energy it's going to produce when it hits a building. Okay. That's an energy problem. Okay. All right. Okay. Any questions on that? Any questions? Okay. Is that pretty cut and dry? That might be a good test problem, possibly. Okay. The rocket problem, that's a good one. Number 12, that's a good one. That was not too bad. Number 15, the Atwood machine, that's a good problem. You got to do some pretty good math there before you get. You got to get your physics right, and then you work it. Okay. Oh man, I don't know if I want to do that one, or I really wanted to get to the ones on one of the handouts. Y'all want me to do the Atwood machine problem? Or do y'all want to try it? I'll tell you what, let's try the Atwood machine problem. What is that, number 15? Pause. Okay. Okay? All right. So what do we end up with? Let's take that equation over there, and we wind up with what? Okay, so we wind up with negative, oh gummit. We wind up with negative M what? BG is equal to what? MBA, right? And then the other equation winds up what? MCA, G, excuse me, is equal to what? MC A. All right. So we've got what? We can factor out a G and say what? MC minus MB is equal to what? Factor out an A. MC plus MB. And then solve for A. Holy smokes. And that should be a subscript, B, but still. Right? Now we can solve for acceleration. Everybody see what I did? And again, where did that come from? T minus MBG is equal to MA, and T minus MCG is equal to negative MA. Multiply through by -1, negative T plus MCG is equal to plus M, and that's B, and that's C, and that's C. Okay? And so those terms are gone, and this is that. All right, now you can solve it, right? All right, now let me ask you something. How do we go back and find the tension? You got it? Okay, good. How do I find the tension in the bricks? Once I find the acceleration, what do I do? Right? Yeah? How do I find the tension in the counterweight? Plug it in. And what happens right here? It's going down. Counterweight's going down, so when we move this across, it becomes positive. That is subtracted out, isn't it? Right? Okay, see if y'all can finish that problem. Okay? See if you can finish it. Sorry I kept you over. Okay? Didn't mean to blow your mind there on that tension, but yeah, tension is tension. Okay? T is T. It's the type of force. Okay? It's the type of force. See y'all at, what, 12:30? Yeah, 12:30.